Hey 12s, can we look here at Simpson's rule today? This is the last part of this topic on integration. And just like trapezoidal rule, what we're looking at is a way of dealing with functions that we can't integrate. Okay, so normally if I want to find the area underneath between this function and the x-axis from a to b, I find the primitive, I substitute b in, I subtract a when I substitute that in, and that tells me the area. Right, that's wonderful. But if I can't find the primitive of this, if I can't integrate that, well, I need to do something else. We looked at trapezoidal rule, okay, that was okay. Simpson's rule is slightly more complicated and slightly more accurate. Okay, we're not going to go into the derivation of this. We talk about it as putting a curve between these points rather than a straight line, the trapezium. That's all well and good. You will get this formula on your formula sheet. It pays not necessarily to remember it off by heart, but certainly to understand the application of it. Right? In this sense here, what we need are, when I'm dealing with Simpson's rule, what I need is the value of the functions at the two bounds and the value of the function halfway in between. Okay, a plus b over 2. Right? The midpoint of a and b, I need that point there as well. Okay, I need to know the value of the function at the midpoint. Now, we subtract the bounds divided by 6. I find the value of the function at both ends and the value of the function in the middle, and multiply that one by 4. Because I suppose you could think about it that that's in the middle. That's particularly sort of important, right? So we have 4 lots of the function in the middle, right? None of the ones on the end. So we need the endpoints in the middle. We've got an example here. We've been given a table of values. We have no idea whatever of the function here, but I do have a table of values, right? And so we're asked to find the area between the function and the x-axis from 1 to 5. Right? Well, here's 1. Here's 5. I need those things, and I also need the middle. I need these ones here. Okay, so for part A here, what we do is the integral from 1 to 5 of function x dx is approximately equal to, right, it's approximately equal to 5 minus 1 over 6, sorry, outside of, now, first one, 2.31, plus 4 times the middle one, 5.34, plus the last one, 0.22. Okay, it's approximately equal to that. If I evaluate that, right, and here's one I prepared earlier, 15.9. And that's rounded. 15.9, 3 significant figures. All good? Right, at that Simpson's rule. Now, we could, it says sort of making the best use of the given data. Well, I could actually use what we say 2 applications of Simpson's rule. Okay, I could use Simpson's rule from 1 to 3, given that I know what it is halfway in between. Could use Simpson's rule again from 3 to 5, given I know the value halfway in between. Okay, so for part B, we're going to take a little bit of space. This is the very last work example for this topic. So, the integral from 1 to 5 of function x dx is approximately equal to, right, approximately equal to, we have 3 minus 1 over 2, over 6, sorry, 3 minus 1 over 6, outside of the first, 2.31, plus 4 times the middle, which is now 4.56, plus the last, 5.34, right? That is approximating the first half of that interval. Right, now we've got to do the same thing for the second part. So this time it's 5 minus 3 over 6, still 1/3, right? We're still multiplying by 30. We'll simplify this. We'll factorize a bit in a moment. From the first, 5.34 plus 4 times the middle, 3.02 plus the last one. Okay, now there's a bit to work out here, but we can see, like, we can simplify this down and I get 1/3. I get 1/3 of this. Now, 1/3 outside of, we've got 2.31, only appears once. 4.56, I've got 4 of them here. Nowhere else. Now the 5.34 appears in this calculation and in this calculation here. So we could rewrite this. And it's approximately equal to 1/3 of, now the first one, 2.31, plus 4 times the next one, plus 2 times the next one after that, plus 4 times the one after that, plus the last one. It is quite an expression. It really is. Now, if we had a whole lot of data here, right, we see that we get a bit of a pattern here. I've always got one of the first and one of the last. I have 4 times all of the even terms here as I go along. 4 times the evens and 2 times the odd ones, right? So if I, in fact, if I had more things in between, don't worry about the numbers 1, 2, 3, 4, 5, but treat them as the first, second, third, fourth, and fifth values. It's the first and the last, 4 times the evens, 2 times the odds, right? For as many of those as we have, right? As many of those as we have, if we evaluate that, we'll get a slightly more accurate answer this time, which should be 14.51. Right. Okay, mess around with that, see how you go. I'll miss you in class, I'm sorry. Shoot me a message. We'll do some revision on Monday. Thanks, guys.